In today's video, we're going to continue our discussion on calculus, but we're moving away from all of our sequences and series that we have been doing. Instead, we're going to learn about something called a parametric curve and how to do calculus with these particular types of curves. So first, we have to imagine what a parametric curve is. So to do that, first just imagine that we have a particle, and this particle just happens to be moving along this crazy curve in space, and it's going in a particular direction around this curve. So this curve C, I cannot write this as a function of x because it doesn't pass the vertical line test, so it's not a function. However, we can write both the x and y coordinate as a function of time. So we can write x is some function of t, and y is some function of t. Where t is called a parameter. And these are called parametric equations. So you can think of this t as time, as I was saying before, and each value of t determines a different xy on this curve, and as t increases, our point xy is moving in space along this path. So this type of curve is called a parametric curve, and the parameter does not have to be time, it just is a lot of the time, but the parameter can really be anything. So let's do an example tracing out a parametric curve. So let's sketch and identify the curve that is defined parametrically. By the equations x equals t squared minus 2t and y equals t plus 1. So we want to pick different values for our t, see what some of these points are, plot the points, and connect, and that will give us an idea of what this curve looks like. So to do that, I'm going to start just by picking some various values for t and see what happens when I plug them into these particular equations. So plug in values for t into x and y to get points to plot. So to do that, I'm going to need to clear my board out so we have enough room. And I would suggest if you're trying to figure out what a parametric curve looks like, you pick values for your t that are both positive and negative. So I'm going to start by picking, I'll go with -2, -1, 0, 1, and 2 for my t. And that will give me values for x and for y. And just as a reminder, x was equal to t squared minus 2t, and y was equal to t plus 1. So I'm going to take these different values for my t and plug them into these equations for x and y. So when I plug in -2 in for my t on my x equation, I'm going to get -2 squared, which is 4, and then minus 2 times -2, so it's going to be plus another 4. So I get 8 for my x. And when I plug -2 in for my y, I get -2 plus 1, which is -1. And I'm going to continue that all the way through. If I plug in -1 into the x equation, I get 3. If I plug it into the y equation, I get 0. And so on. So I plug in 0, plug in 1, plug in 2, and then we can see what this curve looks like. So let me put the points on that I have. I have a point over at 8, -1. So 1, 2, 3, 4, 5, 6, 7, 8. Eight -1 is over here. Then I have 3, 0, 0, 1, -1, 2, and 0, 3. In connecting the curve, it's going in this direction. I get something that kind of looks like a sideways parabola, so you might think that this is a parabola. And we can actually verify that this does give us a parabola if we do what's called eliminating the parameter. What that is rewriting our parametric equations as just one equation involving x and y. So let's see what we get when we try to do that. So, since t is equal to y minus 1, which I get by taking my y equation and solving it for t, we can take that and plug it into the other equation. X equals y minus 1 squared minus 2 times y minus 1. And if I multiply this all out, I get y squared minus 2y plus 1 minus 2y plus 2. Combine our like terms and I get x equals y squared minus 4y plus 3, which is a parabola, just like we thought it would be by looking at it written parametrically. All right, so that's our first example of how to graph a parametric curve. I would suggest if you're trying to graph a parametric curve, just pick different values for t, plug it in to get an idea of what's going on. Make sure you indicate on your graph which direction the curve is traveling. You need your arrows pointing in the direction that the curve is following as t gets bigger. So like this example we did here, I put my arrows going around as my t got larger and larger. So sometimes we actually restrict the values for our parameter. Let me do an example of that. So what curve is represented by x equals cosine of t, y equals sine of t, with t being between 0 and 2 pi? Well, any guesses out there? You might guess this has something to do with a circle. We know our trig functions, we get our values from the unit circle. And that would be the correct instinct to have here, because this actually does give us a unit circle. So for instance, if I plug in 0 for my t, my x will be cosine of 0, which is 1. And my y will be sine of 0, which is 0. So I have this point over here at 1, 0. That's where I'm starting at t equals 0. If I plug in t equals, well, I'll do a pi over 4, your x would be square root of 2 over 2, and your y would be square root of 2 over 2. So there's t equals pi over 4. When I plug in pi over 2, I'm going to get 0 and 1. And it's going to continue along in this manner. So over here at this point will get me my t equals pi. And we're going to get just our nice unit circle traced out. We're traveling around counterclockwise. And my t equals 2 pi gets me back where I started. So we get a unit circle going around exactly 1 time. I should also point out that we know cosine squared plus sine squared is equal to 1. So this also tells us that x squared plus y squared is equal to 1. And that just happens to be the equation of the unit circle. Which is exactly what we got when we plotted this anyway. So it shouldn't be a very big surprise that this is a unit circle. We go around exactly once in the counterclockwise direction. All right, so this is all fine, just drawing some parametric graphs here, parametric curves, but where's the calculus, right? Well, now we get to finally do some calculus with this stuff. So, let us start with talking about finding tangent lines. So let's suppose that f and g are differentiable. And let's say we want to find the tangent line at a point on the parametric curve x equals f of t and y equals g of t, where our y is also a differentiable function of x. Well, we remember from our Calc 1 days that the slope of the tangent line is going to be the derivative of y with respect to x, dy dx. So we're going to use our chain rule to find what dy dx is. So our chain rule says that dy dx is going to be equal to, our dy dt is equal to dy dx times dx dt by our chain rule. And then I can solve this for dy dx, provided that my dx dt is not 0. So I get that my dy dx that I need for the slope of my tangent line is equal to dy dt over dx dt. So what this is saying is that if we need to find the equation of a tangent line and the curve is given to us parametrically, you don't have to eliminate the parameter first in order to find the slope of the tangent line. You can instead use this formula here and get that the slope of the tangent line is equal to the derivative of y with respect to t over the derivative of x with respect to t. And we're going to have a horizontal tangent line if this is equal to 0, which happens when the numerator is 0 and the denominator is not. And we're going to have a vertical tangent line when the denominator is 0, but the numerator is not. None of that should be a surprise. We should also note that if we need to take a second derivative, the second derivative of y with respect to x is equal to the derivative with respect to x of our dy dx. And I get that by doing the derivative with respect to t of dy dx over my dx dt. Where this formula, we get this formula here by replacing our y with dy dx in the previous formula that we had. So we're going to do an example all the way through where we are going to work a lot with tangent lines and concavity of a parametric curve and use that to graph a parametric curve. All right. So an example. A curve C is defined by x equals t squared and y equals t to the third minus 3t. And the first thing we want to do is show that our curve C has two tangent lines at the point 3, 0. And let's find the equations. All right, so first we have to figure out why this curve would have two tangent lines at the same exact point. Well, to figure that out, first thing we should do is figure out what value of our parameter t gives us this point 3, 0. So we have first, let's look at when our y, which was t to the third minus 3t, equals 0, when t times t squared minus 3 is 0. So we get t is 0 or plus or minus a square root of 3. If I take those t values and plug it into x, my x, which was equal to, I just lost it, x is t squared. So if I plug in these values of t, I get x is 0 or 3 or 3. So of course, we're not caring right now about the point where x is 0, but notice that my y is 0 and my x is 3 two different times, when the parameter t is positive root 3 and when it's negative root 3. So what we're saying here is the point 3, 0 arises from two different values of a parameter. Positive or negative square root of 3. So that means if I were to graph this parametric curve, it's going to hit the point 3, 0 two times. It's going to cross itself at that point. So to find the tangent lines at this point, we're going to need the derivative. So we're going to find the slope of the tangent line at t equals plus or minus square root of 3. So first, let's just find what that derivative is equal to. So remember, dy dx is equal to dy dt over dx dt. The derivative of my y with respect to t is 3t squared minus 3, and the derivative of x with respect to t was 2t. So that is what my derivative looks like, and now I can plug in these values of t. So at positive square root of 3, my dy dx is equal to 3 times positive square root of 3 squared minus 3 over 2 times a positive square root of 3. So this is going to be, I have 3 times 3 minus 3 over a 2 root 3. So that simplifies to 3 over square root 3, which is the same thing as square root of 3. So I have at positive root 3, the slope of my tangent line is positive square root 3. At negative square root 3, we have that this slope of the tangent line is 3 times a negative root 3 squared minus 3 all over 2 times a negative root 3. And this simplifies just about the same, except we're going to have a negative in the denominator, so I get negative root 3 for my slope of the tangent line. So now I have two different slopes of tangent lines. One of them is positive root 3, the other is negative root 3. Both occur at that same point, 3, 0. And now I can write the equations of the tangent lines. So the equation of the tangent lines at the point 3, 0, we can get by using our point slope form. And then I can convert it if I really want to. I would get y minus 0 equals my slope times my x minus 3. And so my other one is also y minus 0 equals my other slope times x minus 3. That's in point slope form. If you wanted to distribute, you could. I personally wouldn't bother. I would just leave it in point slope form. So I have these two tangent line equations at the same exact point. All right, so we found our first tangent lines of a parametric curve. Let's see what else we can do with the same example. So part B, find where the tangent line are horizontal or vertical. So remember, your tangent line is going to be horizontal when it has a slope of 0, and it's going to be vertical when the slope is undefined. So let's write down what we found for our slope of tangent lines. Remember, our dy dx was equal to 3t squared minus 3 over 2t. So this is going to be horizontal when the numerator is 0, but the denominator is not. And it's going to be vertical when the denominator is 0 and the numerator is not. So first notice that, let's do horizontal first. My numerator equals 0 exactly when t squared is 1, which is t equals plus or minus 1. So I have two values for my parameter where my tangent lines are going to be horizontal, but this does not tell me the points where it's horizontal yet. To find the points where the tangent line is horizontal, I have to plug my parameter into my equations for x and y. So I have horizontal tangent lines. When t equals 1, I get my x is equal to t squared, which is 1, and my y is equal to t to the third minus 3 times my t. So my y is equal to 1 minus 3, which is negative 2. So I have a horizontal tangent line at the point 1, negative 2. This was where my t was equal to 1. And now to figure out what the point is when my t is negative 1. When my parameter is negative 1, my x is going to be still 1, and my y is going to be negative 1 plus 3, which is positive 2. So I get a horizontal tangent line at the point 1, positive 2, which was where my t was negative 1. So I have two places where I have a horizontal tangent line, the point 1, negative 2, and the point 1, positive 2. Now finding where I have a vertical tangent line, that was where my denominator for dy dx is equal to 0. So vertical tangent line was when my denominator of my dy dx is equal to 0. My denominator was 2t. That happens when t is equal to 0. And if I plug t equals 0 into my x and my y, I get x is 0, and y is also going to be 0. So I have a vertical tangent line at the point 0, 0. That was when my t is equal to 0. All right, so now I know I already have my two tangent lines at the point 3, 0 with the equations that we found before. And I have a horizontal tangent line at two different points, 1, negative 2, and 1, positive 2. And I have a vertical tangent line at the point 0, 0. Now let's figure out the concavity of this parametric curve, and then finally we'll put it all together and sketch it. So part C, determine where the curve is concave up or down. And we have to remember that we need our second derivative for that. And our second derivative of y with respect to x is equal to the derivative with respect to t of my dy dx over my dx dt. Now, we already know what dx dt is. We already did that when finding just our first derivative. My dx dt is 2t. Now, for this numerator, I have to do the derivative with respect to t of my derivative. So that one we're going to have to use a quotient rule on. Let me write this out. I have my second derivative is equal to the derivative with respect to t of what I had for my first derivative. 3t squared minus 3 over 2t. I need to take the derivative of that. And then my dx dt, which is in the denominator, that's still 2t. So simplifying this, first take the derivative up in the numerator here. I need a quotient rule for that guy. So I'm going to have my low times d high, the derivative of the top, minus my high d low, derivative of the bottom, square the bottom, and away we go. There's my quotient rule. And I still have this other 2t in the denominator here. And so we're going to just have to simplify this guy, which in my denominator, I'm going to end up with an 8t to the third. And in the numerator, if I distribute everything and combine my like terms, I'm going to get 6t squared plus 6. So simplifying, we get 6t squared plus 6 over an 8t to the third. Which if I wanted to, I could factor this. and get 6 times t squared plus 1 over 8t to the third. So this is my second derivative. Remember back from Calc 1, your graph is going to be concave up when the second derivative is positive, and it's going to be concave down when your second derivative is negative. So first, look at this second derivative. My numerator is always going to be positive. 6 is positive, t squared is at least not negative, and when I add 1 to it, it's going to be positive. So the numerator is always positive. The denominator, well, it's going to be negative when t is negative, and it's going to be positive when t is positive. So I have concave up when my t is positive, and it's concave down when t is negative. All right, so now let's try to put together all of the pieces that we've done and draw a sketch of what this curve looks like. So part D, we're going to sketch the curve C. So things I need to remember. Let me put my points on this curve. I have a point at 3, 0. I have 2 different tangent lines there, and they go in opposite directions because their slopes were opposite. I have a point up at 1, 2, where we had a horizontal tangent line, and a point at 1, negative 2, where I have a horizontal tangent line, and I have a point over here at 0, 0, where I have a vertical tangent line. And then we also have to think about what direction this curve is going to go in. So first, remember, you have 2 tangent lines here with opposite slopes. And if I trace this stuff around, this point up here was where t was equal to negative 1. This guy down here was t equals positive 1. And this one was t equals 0. So I'm going to be going in this direction. This is a very, very rough sketch. But notice I have my horizontal tangent lines where I need them, vertical tangent line where I need it, my 2 tangent lines at the point 3, 0, and we get that sort of a shape. Notice that when my t was negative, which was everything until I reached this point at 0, I am concave down. And then after 0, I'm switching to concave up, so it matches that information as well. All right. So one last thing that we really need to talk about on this particular section is now we need to talk about how to find the arc length of a parametric curve. Hopefully you remember how to find arc length in general. That's something we learned in this class. So let's do a reminder of that first. So remember, the length L of a curve given by y equals some function of x, where my x is between a and b, is given by L equals the definite integral from a to b, square root of 1 plus my derivative squared with respect to x. Hopefully that looks familiar. That's something we did earlier this semester, finding arc length of a curve. But now let's just suppose that we have a parametric curve rather than a curve just defined as a function of x. So let's suppose a curve C can be described by y equals f of t, sorry, x equals f of t and y equals g of t, with alpha less than t less than or equal to beta, where my dx dt is greater than 0. So we have our curve traversed exactly once, left to right. F of alpha is equal to A. F of beta is equal to B. Then what we have is our arc length formula that we wrote down earlier. My L, which is equal to the integral from A to B of a square root of 1 plus my dy dx squared with respect to x, I can rewrite this as an integral from alpha to beta of a square root of 1 plus the expression that I have for my dy dx. That was dy dt over dx dt squared dx dt dt. Now, that looks pretty terrible right now, I fully admit that, but it actually writes out pretty nicely. Now, since we said that our dx dt is bigger than 0, we can rewrite this in a nice way. My arc length is equal to an integral from alpha to beta, square root, dx dt squared plus dy dt squared with respect to t. Now, it is important that when we set up this formula, we're talking about how our curve is traversed exactly one time. So you do need to make sure that if you're trying to find the arc length of a curve, make sure that it's only traversed one time in the equations that you're given and not that it's going around multiple times. Otherwise, it's going to give you an arc length that's a multiple of what the actual arc length is. So let's do an example. Find the length of the unit circle given by x equals cosine of t, y equals sine of t, where my t is between 0 and 2 pi. So this is the same expression for the unit circle that we had before. This is going around exactly one time on our unit circle. So I should be able to use my formula. So notice that my dx dt is equal to negative sine t, and my dy dt is equal to cosine of t. So if I take my arc length formula, I'm going to get that the length of this unit circle is the integral from 0 to 2 pi of the square root of my dx dt squared plus my dy dt squared with respect to t. So underneath the square root, I have sine squared plus cosine squared. The negative goes away when we square it, and we all know sine squared plus cosine squared is equal to 1. So I have an integral from 0 to 2 pi of the square root of 1, which is 1, dt. If I do this antiderivative, I get t, and I'm evaluating at 2 pi and 0. So I get that the length of the unit circle is just 2 pi, which should be expected. We're just going all the way around our unit circle one time. We know that there's 2 pi radians going around that circle. All right, so that is about it for today. We are going to be moving on to something called polar coordinates in our next video. Uses a lot of the ideas from our parametric curves, but it's a whole brand new coordinate system that you may have never seen before. We're going to do a lot of really fun graphing in that next video, so I hope you come back to see it. If you have any questions, you can feel free to drop them below, or you may email or come to office hours if you're one of my current students. And I will see you in the next video for polar coordinates.